Unit 2. In a few days here, we're going to be talking about Venn diagrams. And so here's a Venn diagram, which I'll zoom into. Kind of a humorous one. Hopefully you understand that there's three main regions here, and there's overlapping going on. And we'll talk about these. And hopefully you will be in this group, right? All right. Just a little bit of humor. And here's another one here showing you the traditional phrase, how's it going, and your response. And such a small overlap between those that are actually fine. We're going to close up with a Powerball, and we'll look at the probability of that one. But let's start, first of all, by defining what does probability mean. All right. Well, notice we have to count outcomes. We've been spending a whole chapter, practically, in Unit 1, learning to count outcomes. In this case here, you are counting favorable outcomes to possible outcomes. Okay? So keep that in mind as we move forward here. Favorable over possible. Another name for possible is sample space. All right, there are three main objectives for this particular unit. Number one, you need to know how to calculate and write a probability. Number two, we're going to use this word, what we call chance or random behavior, and we need to understand a little bit about what is going on there. And to help us that, we need to use and lean in on a law called the law of large numbers. And we'll be doing an experimental and theoretical probabilities and using those probabilities. All right. First of all, writing out probabilities. First of all, the values are between 0 and 1, always. Rarely do we come across in life things that are actually 0 or actually 1, but in reality, theoretically, you could get those values. Now, the way we write them out, you can do in fractional form, what we call ratio form, or as a percentage, or you could write them out as a decimal. So here we're starting one with a decimal, and changing that to a percentage shouldn't be too tricky. Writing it as a ratio, a little bit tougher. So we first of all put it over 100, and then make sure that you reduce it down. All right. Of these, I would say the simplified ratio is probably the easier way to get most of the time. All right, let's look at a spinner here and look at how do we write out probabilities. First of all, note the letter P and then after it in parentheses. This means what is the probability of landing on red? All right, and if we look at the picture, we see that 1/4 of the circle is pictured red, so 1 out of 4. Again, you don't need to change that to 0.25. You can just leave it as such. The probability of blue, identical, also 1/4. The probability of yellow, well, that's smaller. That looks now to be about a half of the 1/4. So that would be 1/8. And then the green, well, how much is left over? If you take out 1/8, and this is 4/8 total, why then you have 3/8 left. Finally, we're going to use a symbol. It is not, and it's going to be used as a little tilde. So this can be thought of as not red, or sometimes we put a little C up here, and that means the complement. Okay, so please take note of that. That should be in your notes because that is going to be new to all of you. All right, what is the probability of not being on red? Well, hopefully you see that if red is 1/4, then the rest of it is 3/4. Okay. Well, let's look at a die. What is the probability of getting a 2? Well, the 2 shows up on one side, So the favorable outcomes, there's one favorable outcome, and then there's 6 sides of a die. Again, you can't reduce the 6 or the 1, so we just write it as 1/6. If it says even, make sure that you count up how many evens are there, and then don't forget 3/6 reduces to 1/2. Again, something with probability of greater than 4, that would be 5 or 6, so there's 2 of them. So then we have 2/6, which would be reduced to 1/3. Yeah, that shouldn't be 3/6, that should be 2/6, and that should be 1/3. Okay. Probability of 3 with a C. Again, that means the complement of 3. So what are things that are not 3 on a die? Well, that would be 1, 2, 4, 5, 6. So there's 5 of those things. And again, there's 6 sides, so 5/6. What about something crazy like not a 7? Well, there's no way you can get a 7 here. And so the probability of getting a 7 would be 0%. So the probability of getting not a 7 would be 1. Again, you can write it as 100% or merely just 1. Now let's look at CIHS enrollment. This isn't accurate results from this year, but from a previous year. But they're close to the numbers that we currently have. If we have 448 freshmen, sophomores, juniors, and seniors, we add those numbers up, we get a nice number like 1,600. So what is the probability that a student would be a freshman? Again, that's a bad would. I think there was a joke that Mr. Metz was making there. Anyways, so the probability of being a freshman would be 448 divided by 1,600. It's approximately 1/4. That ratio reduces. You could divide them both by 2. You get 224 over 800. We do it again, and we get 112 over 400. I think we can do it one more time, and we would get 56 over 200. Looks like we can keep going. 28 over 100, so that's 28%. 14 over 50, or 7 over 25. Now this was a long way to get the ratio, but just to show you how that process is done. If it says not a senior, then we would have to add up all the ones that are not a senior, so that would be those. And again, that looks to be about 1,264 over 1,600. Again, you could go to your calculator, multiply that out. That's going to be, I think, well, I don't know what it is. I can't do that mentally. Moving on down the road. Power jackpot. How do we know what is the likelihood of being the winning ticket? Well, we did the math the other day, and we would have 69C5 as the total number of possibilities. Plus, remember, we have the Powerball itself, which is one number out of 26. So we multiply those two numbers together, and then we would divide by that number, because that number there, and I don't have a calculator and I'm stuck on my chair, so I'm going to let you calculate that out, but it would be one ticket out of that many million. And it seems to me that number was in the neighborhood of, let's see, I think I actually got that number here. Review. So 11,233 times sorry about that, times the 26, so whatever that is, times, so I don't know, I'm not going to figure that one out mentally either, but divide those two numbers and that's your probability. Again, writing that as a ratio is probably simpler than trying to get a calculator and multiply that out. divide that out. Sorry, we'll skip those 2 slides. Finally, we're getting to this word random. What does that mean? We use that word casually in everyday life in many different instances. In mathematics, we say that this is not a pattern that we know. All right. Student looks through their closet to decide what shirt to wear to school, right? Is that random? No, it's not. It may seem random, but it's not, because people choose things based upon a lot of different reasons. How about labeling the 6 pairs of shoes with 1 through 6 and then rolling a single die to decide which pair to wear? That's pretty close. It would be tough to predict that. We wouldn't necessarily have a predictable pattern unless we knew how to throw the dice the same way every time. The state legislature deciding to increase funding by schools, even though it's unlikely that we see increases in funding, we don't want to call that random, because again, though we don't know how the legislature works, this is, predictable based upon who's in the Senate, what party controls the Senate, that kind of thing. All right, based on how much funding there is. So, a professional golfer making a hole-in-one. Again, not entirely random. It is unlikely, but it's not random. If somehow you could spin somebody around on the tee and have them shoot at, random directions and then get a hole-in-one, that would be more random. You go to the phone book, close your eyes, and point at a name. It's somewhat random, but entirely not, because not everybody owns a phone. And so right away we don't have a true random population. And we have a tendency to pick certain spots in the book, like in the middle, not at the top or the bottom of the book. So again, we will be working with what we call random numbers, and there are random number generators, and those are close to random. They're not exactly random, but thereabouts. All right, funny face there. So now looking at a situation of tossing a coin, except I'm not really going to toss a coin. Instead, I'm just going to look at some numbers for my tosses. So let me show you how I'm starting to tally this up. So here I've got 5 numbers, and I'm looking at that numbers as 5 tosses. And the way it's a toss is I decided ahead of time that an odd number would be a, what did I say? An odd number would be a head, and an even number would be a tail. So you can see here we have 4 tails, 1 head. And then we have 2 tails and 3 heads. So you can see those tally marks here, 4 and 1, 2 and 3. Yeah. And so I'm just going to fill this in. And then to the right of that, I'm going to tally up what the cumulative total is. So if we started off with 4 heads and 1 tail, that was weird, odd. Then we had 2 more. So I'm going to say 6 and 4. And then we have 2 more, and we get 8 and 11. Now notice how initially we had a ton more heads than tails, but that gap is closing. If we look at the next one, we have no tails. All we have is 5 heads, because they're all even. So, or tails, sorry. So the tails jumps up 2, and we have, oops, that should be 7, not 11. I don't know where the 11 came from. 12 and 8. And I look at the next set, and that would be 1 and 4. So I'd have 9 and 16. And then we have 3 and 2. And so that would be 12 and 18. And then another 3 and 2. So we have 15 and 20. And then we have 2 and 3. And so we would close with 17 and 23. All right. And notice how these numbers have gotten closer and closer as we kind of went further. If we would do this more and more and do this 1,000 times, these numbers would get really, really close to 50% each. They would never get precisely. But if I were to take, 17 divided by 40, compare that to 4 divided by 5, or 1 divided by 5, my bottom numbers would be closer. So this is called the law of large numbers. And what that means is if I do an experiment, the more I go, the larger number of tries I do, the closer I get to what we know would have to be the actual probability. All right? That's, again, the law of large numbers in experimental probability. All right, here we have a grid showing us the sum of the die, of two die, excuse me. Here's our second and our first die listed, and then the sums on the inside. So what is the probability of the sum of a 3? Well, I see a 3 comes up in 2 places. And since we have 36 total squares, can't even zoom in here, then I would say 2 out of 36, which reduces to 1/18. Okay, sum of a 12, well, only 1 out of 36. And we can see that 7 is the most popular roll to get. And so 6 out of 36, which would be 1 out of 6 rolls would be a 7. Okay? Now what if you roll the die 20 times? What is the probability that the item would be, let's say, a 7? How many of those rolls would be a 7? What we do is we take 20, that's the number of rolls, times the probability of the event, 1/6. So this would give me 20/6, which would be 10/3. And if I multiply that out, I get 3.3 repeating, which tells me somewhere between 3 and 4 times I would get a 7. Okay, it's a pretty popular number to get when you roll 2 dice. All right, and again, we could roll the die and see if that in fact happens. If I did it 200 times, I would get really close to this. And the reason I know that is that this is the theoretical probability and this is the experimental probability. And so anytime I do it, I will get varying numbers, but the more often I do it, the more I'll get closer to the theoretical. All right, game of pool. Yeah, don't know if you've played before, but there are solids and stripes. And there's a total of 15 balls. What is the probability that the ball is yellow? Well, hopefully you can see that there's 2 balls that are yellow, so 2 out of 15. What is the probability that it's striped? Well, there are from 9 to 15. Again, that's 7 balls that are striped, so 7 out of 15. And if it's greater than 10, why then the dice, again, that has to be 11 through 15. And there are 5 there. So again, you start off by writing 5/15, and that reduces down to 1/3. What about not striped? Well, again, that would be 8/15. All right. So we've kind of gone through that. Let me just do one last example here with cards. What is the probability of getting an ace? Well, hopefully you know that there's 52 cards in a deck, standard. So 4 of them are aces. So we're going to say 4 52nds, which is 1/13, excuse me. If I divide them both by 4, that reduces down, right? What about a club? Well, a club, there's 13 of them, so 13 52nds, but that reduces down to 1/4. And a black, well, there's half of them are black, half of them are red. An 8, that's a lot like the ace. for 50 seconds. Face cards, that would be the king, queen, and jack. So there's 3 of them in each suit. So I take 3 times 4 and I get 12. So there's 12 favorable outcomes and 52 non-favorable. Again, reducing that ratio down, I get 3/13. Okay? Selecting numbers randomly from there. What is the probability it's going to be even? Again, you would count them up. There's 7 even ones out of 15 total. There's slightly one more odd one. Okay? Most of us, if we had to pick randomly from the list, we wouldn't pick randomly. So that's a very dangerous way, again, to pick random numbers. But given a list of numbers, right? You know, prime, how many primes are there? There's 6 prime. I think they're the ones that are underlined. They're all divisible by 2, so that's 15 out of 15. All right. And sometimes they'll give you a picture, and they'll say, what's the probability you pick a red dot of the dots that are there? Well, you count up the total dots. There's 15. How many of them are red? 7 are. Hopefully you can see those 7 red ones. Or the brown ones, that there's only 1 brown solitary one. I think it's right there. Or purple. Kind of hard to see those dots, yeah? Okay. Well, hopefully right now you are feeling fairly comfortable about converting back and forth between fractional, decimal, and percent forms. You know a little bit about what it means to be random, and using those random numbers like I did in that one set of problems where we flipped a coin, and we didn't actually flip it but used random numbers to describe that. And then the effect of doing a few experiments versus a large number of experiments, and that takes us closer to the theoretical probability than the experimental probability, which starts off really weird because, again, random numbers will give us weird results initially, so we have to do lots of them.